Okay, so I suppose I'll start. I welcome the viewers to this problem solving and live interaction session for the subject engineering mechanics, which is offered by Professor K. Ramesh in the Swayam portal. So today we will be looking at contents from week 8, which has to do with absolute motion and some rudiments of relative motion. Mainly, we will be focusing on non-rotating translating axis, which could or could not have acceleration. Okay, so if I were to look at the first question, so the first question says, the paths of 2 points P and Q on a rigid body undergoing general plane motion are as shown. Are shown. Essentially, there are two paths which are shown. Identify the correct relative velocity Vp with respect to Q. So when we write this, we have discussed in week 1 also that when we write this, we imply that the origin is fixed at Q. So we want to write v of p with respect to q, velocity of p as seen by the observer at q when a set of non-rotating translating axes. So we have also qualified how the observer is attached to q, whether the observer is rotating with the body or not rotating with the body, just translating at q or not. Okay, so let us look at this uh, first from another angle. So let us say that there is some rigid body. Let me not draw it to be an okay, let it be an ellipse, for example. So how we go about analyzing the motion of this body is what we are trying to see. So initially we will be having some fixed reference frame which is attached to the ground. Let me call that as capital X for simplicity and capital Y. And Z comes out of the plane of the paper. Okay. So now initially what we do is we take one point, any arbitrary point, let us say some q. And then with respect to the fixed atom, we draw the position vector to q. Now in order to characterize the motion of any rigid body, we need to know the velocities at least 2 points so that we know if those are parallel, if those are congruent, parallel, and exactly the same, then it implies that the rigid body is undergoing translation. It could be curvilinear or rectilinear translation. If there is difference in those two velocities, then it implies that it is undergoing rotation. And if one of them happens to be zero and the other one is having a non-zero value, it implies that it is a fixed axis rotation. Otherwise, it could be classified as general plane motion. So let me take another point P. Let me take this point P and let me draw the position vector like that. Now what I have done is, let me take this to be the non-rotating translating axis. So this is small x, small y. Now we have to understand this clearly that I am fixing this at q. Now the only constraint that is placed on this axis, the non-rotating translating axis, is that it cannot rotate with the object, but it can definitely accelerate. So it is to be understood clearly that non-rotating does not mean that it does not have acceleration. So it is not an inertial frame of reference. It may well have acceleration, but that acceleration would have to be linear. Okay, so I have attached this now to that uh, point q, and I look at the position vector of p. So this is essentially rp, and I have this as rq, and this green one is rp as seen by q. So from simple law of vector addition, I can write this as rp is nothing but rq plus rp with respect to q. Now that I have written the position vector, I can take the time derivative and get the velocity vector. So that implies that velocity of p is nothing but velocity of q plus the change in this vector, time rate of change of this vector, whole dot. Now this vector, how I can represent this? With respect to x and y coordinate, I can represent this as some r p with respect to q can be written as some rxi plus ryj with respect to the black axis. Or I can, another way of writing it as rp, let me call this distance, let the magnitude of rp with respect to q be represented as r, just without any symbol, without any subscript or anything. So that means that r p with respect to q vector can be represented as r er, where er is that is er cap, and that is e theta cap. So we can see what is er cap. I need not draw e theta, it is just a perpendicular component of that. So RER. So substituting this here, what do we get? So velocity of P, let me add one page here. So let me take this over there. So how can I write this? So velocity of P is nothing but velocity of Q plus R ER whole dot, the time derivative of the entire thing. So this will give me again velocity of Q plus, if I were to apply product rule, it will be R dot ER cap plus R ER dot. So I've just split and applied the product rule. Now we know, by virtue of this being a rigid body, this gives that r dot is actually 0. So therefore, velocity of P is velocity of Q plus r er dot, and we know that er dot is nothing but omega e theta, r omega e theta cap. So this nothing but as equation for the velocity, for finding out the velocity of a point P in a rigid body with respect to another point Q on that rigid body, where omega is nothing but the angular velocity of that rigid body, and r is the distance between these 2 points. So we can see that this is a degenerate case of a circular motion. So this is why we initially studied circular motion and then we graduated to rigid body mechanics, where first of all we will gauge from the mechanics of the problem, we will gauge velocity at least one point in the rigid body with respect to the fixed reference. Then we look at another point. We gauge the velocity of one point in the rigid body. Then we sit at that point with a non-rotating translating axis and look at the other point P. When we look at that other point P, it will appear to trace a circle. It will travel in a circular path because of the fact that the body is rigid and the distance between these 2 points are fixed. It does not change. So similarly, now when once I have got the velocity, I can naturally take the acceleration also. So acceleration of the P, that it follows that it will be acceleration of Q plus I just have to take the time derivative of this r omega e theta cap, the entire time derivative. So it is just a matter of doing it step by step, which we have done in the last session also, if you see that video. But nonetheless, let me do it for completeness. So it will be AQ, acceleration of Q, plus R dot omega E theta cap plus R. I'm just differentiating one at a time, keeping the other two constant using the product rule of differentiation. So this is omega dot E theta cap plus R omega E theta cap dot. Now one thing we must notice, in the last session I would have written ER cap dot as theta dot. Instead of theta dot, I'm writing it as omega, which is the same thing. Angular velocity is either can be represented as the time rate of change of theta, or I can simply represent it with a new symbol as omega. Similarly, we will represent omega dot with a new symbol as alpha. Okay, now I know that this goes to 0. This is 0 by virtue of that being a rigid body. So acceleration of P, this comes out as acceleration of Q plus R alpha E cap plus R omega squared E R. How this came about? We know that ER dot is omega E theta cap, and E theta cap is nothing but minus R omega E R. So essentially this should be minus. So we can see this is nothing but the tangential acceleration of that point. So when we look at circular motion, we are setting at Q, we are looking at P. It appears that it is having a tangential acceleration and a centripetal acceleration. Now tangential acceleration could be 0 in some cases where it is rotating with a constant angular acceleration, but this will invariably exist because it is constrained to move in a circular path by virtue of r being constant. So we have got the acceleration equation also. So what we understood as circular motion is starting to appear in rigid body mechanics also, because r happens to be constant. So what we try to do by this relative motion analysis is we try to take a point whose velocity we can gauge with respect to the fixed frame. Then we attach a non-rotating translating axis. This is just a matter of convention. I can take it in polar coordinates, or I could have taken I and J Cartesian coordinates also. It is just that the time rate of change would be different. That is all. But ultimately, the answer has to come out to be the same. And if we have to add two vectors, then they have to be represented in the same basis, same vector basis, either Cartesian or polar or cylindrical polar. So what is the moral of this story? It is that if we have a rigid body and we try to analyze its velocity, the kinematics of that rigid body, essentially its displacement, its velocity, its acceleration, then towards the end we will try to locate it, we will try to relate it to kinetic quantities such as forces and moments, couples, torques. So once we do that, then we are in a position to design mechanisms. So given a force, what will be its acceleration? Or given an acceleration, what would have been the force applied? And the rotational analogs of these two. So that is what we are trying to build upon. So this is the essence of our relative motion analysis. Now, where it becomes more and more complicated is how we attach this axis, the black axis which I have attached to Q. Whether it is rotating with the rigid body or it is simply translating is the entire question. So if it is just translating, we label that as non-rotating translating axis, which is very different from an inertial frame of reference. It must be understood clearly. Just because it is non-rotating does not make it inertial. Excuse me, there is some work going on here, so there might be some disturbance. I apologize for that. Now, if we have this xy axis that is fixed to q as just translating, then we will be deriving relative motion in this way. Now, if it so happens that it will be rotating, which we will see in the next week, then we will have some additional terms here. So there will be some additional terms to this which we need to account for, because the xy itself is now rotating. So that is all there is to it. Okay, now that we have seen this brief, let us come back and look at this question, which is pretty simple in that sense. Identify the correct velocity p with respect to q. So if this is r, what I'm saying is q's motion I know. Q is moving along this path. Now sitting at Q with a non-rotating translating axis attached at Q. With a non-rotating translating axis attached at Q, what will be the velocity that I perceive of P? I know what will that velocity be. It necessarily has to be a circular motion kind of thing because R is fixed. So E theta, if we see, it has to be perpendicular to R. So if we take this to be R, it necessarily has to be perpendicular. So at best, it can be either that way or that way, depending on how the motion is. Now we can see in this case, we actually have circular motion that is coming in. So this is our correct answer. Similarly, if we were to fix it at P and observe Q, then this thing will be just the opposite of this. It will just be the opposite of that. So this is velocity of P with respect to Q, and the green one is velocity of Q with respect to P. Let me not put it in green because we have used that for some other discussion. Let me put it in some blue, dark blue. Okay, so I take it that this is clear. Excuse me. So this question asks, a person looks at the paths traced by two arbitrary points, A and B, on a rigid disk and observes the paths to be concentric circles with some common center here after time t. So the question is asking the rigid body, which is this disk, is said to be undergoing which type of motion, whether it is rectilinear translation, curvilinear translation, fixed axis rotation, or a general plane motion. Now we can clearly see that this is nothing to do with rectilinear motion. Now let us try to understand this. We have at time t equal to 0, this is the rigid body. At time t equal to some t1, it has moved from here to that point along that circular path. But if we were to look at displacement, it only cares about the final and initial points, not the path taken. So this is the initial position. This is the final position, not completely. After going here, I would have to rotate it like that in order for me to get the final position. So this definitely involves translation of point B and then a rotation. So this is translation and then a rotation. So we know that whenever there is a translation and a rotation, it has to be classified as general plane motion. Now there could be a question, why, if it is actually tracing a circular path, why can't I say that it is curvilinear translation with that curve being a circle? That could be one question. Now how it would have looked if it was curvilinear translation, let us see. This is what is actually happening. This is general plane motion. So this is general plane motion. Now let us see how curvilinear would have looked. This is at time t equal to t naught. Now at time t equal to t1, it would have gone there like that. Because we are saying it is having only a translation. This is the displacement, but it is essentially having a translation like that. So that will be the final path. After some time, it would have come here. So now, if I were to join all the points, all the point A, where all does it fall? Now I can clearly see it. This is the path point A would have taken, more or less. I'm not exactly able to make it sit in a circle, but I suppose you get the idea. This is the path of point A. And if I were to duplicate this and then make it in some other color, let me use this color instead. This is path of point B. We can see point B seems to pass through this path. So we can clearly see that it is not congruent circles. It is essentially congruent circles, not concentric circles. That is why this is not curvilinear motion, because it is having no rotation. Essentially, all the velocities are the same invariably. So this is the velocity. At this point, this is the velocity and this is the velocity. So both are same. Whereas in the first case, if we see, its velocity is this way and the velocity of the other point is also parallel to that, but with a lesser magnitude, because it has to trace a smaller circle while still maintaining the rigidity of the object. That is why the velocities are different, hence it is also undergoing rotation. So it is not curvilinear translation, so we have justified that. Now one can also ask the question why it is not fixed axis rotation. Now if it so happened that we were treating this as a planet, let us say, around some center, we will only be concerned with the mass point of that object, and we will say, so the mass point will be having some velocity like that, which is what we did in the previous week's problem on that car going around a circular path. We were only treating that as a particle and we were only trying to observe the mass point. So in such a case, this can be considered to undergo fixed axis rotation about that point. But we are talking about a rigid body where we have qualified that there are 2 points. And we are trying to look at these 2 points. So once we look at these 2 points, it is necessary that these concentric circle which it traces, the center of that has to be confined to that rigid body. Only then it will be undergoing fixed axis rotation. So let me also clarify that how fixed axis rotation would actually look. If we said that the body was undergoing fixed axis rotation, so this is at time t equal to t naught, at time t equal to t1, it would have been like that. At time t equal to t2, it would have been like that. Let me erase that. At time t equal to t2, it would have been like that. But at the same point, that is when it will undergo fixed axis rotation. So this is the case of fixed axis rotation. So it depends on how we are trying to study the problem. Now let us say that we are trying to analyze planetary motion. So the motion of the Earth around the Sun, we can treat Earth as the particle with its mass center at our interest, and we can try to see its velocity around the Sun. Now when we come pay our attention to the planet Earth itself, and then we try to look at 2 objects, then the attention is totally different. Then what we are trying to study is totally different. So once we have qualified 2 points on that rigid object, it is obvious that we are trying to study the motion of that rigid object. And the mass center would have a velocity which would have been brought about by some external source. So that is what it is. So I hope that that is clear. So this is fixed axis rotation. Let me put that here. This is curvilinear translation. And then we have our general plane motion, which is the actual case here. So let me remove this. So I take it that this is clear. Okay. Now it is important that I also mark that point where blue is the axis of rotation, which is confined within that rigid body. Okay. Now let us look at this question. It says two disks are connected such that the disk C rolls over the perimeter of the fixed disk D without slipping. So we have a fixed disk here. This is my fixed disk. And then I have my smaller disk here, which rolls over the perimeter of the fixed disk without slipping. So at time t equal to t naught, it is like that. And let me mark 2 points here, blue and green, black and green. I have marked 2 points here, black and green. So this is at time t equal to t naught. Now at some other time, at t equal to t1, what is the case? It would have moved here and it would have rotated like that. Now we can clearly see when we mark 2 points on that disk, how they move. We can clearly see that. Okay, so identify the correct statement. The disk is undergoing general plane motion. We just saw that this disk, it would have been here, it went there, and then it rotated. Essentially, both were happening simultaneously, but we can decompose that into two separate actions. So, yes, the disk is undergoing general plane motion because it is rolling without slipping. The connecting rod is undergoing what type of motion is what is asked. So let this be the connecting bar. Let me take it here. And then at time t equal to t1, it is like that. So I can see that the connecting bar has its center of rotation here at point B. And it is just sweeping a circle. So essentially, it is undergoing fixed axis rotation. We can see that because the point is confined within it. If it were outside, it still will not be curvilinear translation. It will be general plane motion. So I take it that this is clear. So this is clearly incorrect. It is actually undergoing fixed axis rotation. Disk C is undergoing curvilinear translation. Now that we have identified it is undergoing general plane motion, it certainly cannot be true. The instantaneous point of contact between the disks has zero velocity. Now the question says, let me copy and put it here as the reason for why this is because it rolls without slipping. So as it is discussed well in the lectures also that when it rolls without slipping, this point This point is my instantaneous center of zero velocity. Because this entirely does not have any speed, any velocity, so this is trying to roll. So my velocity at this point is like this. At this point it will be like that, with this point, the point of contact, as the instantaneous center of rotation or zero velocity. So yes, this is correct. Okay, so far we have looked at abstract examples where we try to identify the motion and qualify it. Now let us try to solve some numerical problems also, so that we get the confidence in doing the vector analysis. So the question says, this is a link we have. A link PQ slides along an inclined wall and a horizontal floor. So we have one inclined wall here, and then we have a horizontal floor here. Both the floor as well as the wall are smooth and frictionless, so we need not consider friction as of now. At the instant depicted, it is known that the absolute velocity Vp is 3 meters per second in the direction shown. So for this point, excuse me, there's a power cut. So I have been given the velocity of this point as Vp. Now from the figure, I can see that this point's velocity is given as Vp, which is in that direction. Okay. And it has a magnitude of 0.3 meters per second. So answer the following question is what is asked. Now let us try to first analyze what is it that we know. What do we know from this problem as of now? We know that this link is rigid. So this 1.2 has to be fixed. 1.2 cannot change. We know that this thing never loses contact with the floor on the or the wall. Nothing of that sort has been specified. We know the velocity of point P is like that. Now, by virtue of that not having lost the contact, we know that the velocity of point Q has to be upward and it has to be parallel to this wall only. It invariably has to be parallel to that wall, either up or down. But since this is moving to the right, naturally we can guess that Q is moving upwards. So if I were to represent this vector, unit vector in that direction by n cap, I know that my velocity of Q is along n cap. That is something I know. I don't know what is the magnitude of that, but I know the direction. It will be along n cap. So from the question, can I write n cap? So n cap, if I were to see that this makes an angle 75 degrees. Let me take my axis like that. This is x. This is y. Now this is my axis. If I were to place my axis here, then I can see that n cap is nothing but cos 75 I cap plus sin 75 j cap. So I know the unit vector there. Now any vector can be, we know that any vector can be represented as, so I know the unit vector there. Now we know that any vector can be represented using the magnitude and its unit vector. So what can I write about velocity of q? If I take it to be vq, if I take vq to be the magnitude, then I can write this. This is my velocity of q with a magnitude of vq which is unknown and along n cap. So I can write VQ vector as VQ cos 75 I cap plus VQ sin 75 j cap. So this much I know. This much I know. I don't know the magnitude, that's fine. But about VQ, I know this much. About VP, what do we know? VP, we know it as 0.3 I cap. It has no J component. I can clearly see that it is having only a horizontal velocity at this point. So this is something I know. This is also something I know. Now, if we look at our discussion, what we did earlier, essentially, when we take a rigid body, we will take one point whose velocity can be gauged, and then we'll attach a non-rotating translating axis at that point, and then look at the other point, and that other point will appear to trace a circular arc. Now, let us look at this graphically first. So, I have this as my vector. Let me take a copy of this and put it here. I'll remove this. So I know that my velocity finally has to be like that. I have my velocity of P like that. So what I do is I make velocity of P to go like that. And then it rotates. So it has to be perpendicular to this. So if I draw velocity perpendicular to that, this is nothing but velocity of Q. Is it point Q? Yeah. So this is velocity of Q with respect to point P. That is that vector, which is at a distance of, which is 90 degrees to this. So if I take it here, we know from vector addition that I have to put it like that, tip to the other. And then it finally gives me n cap. So this is nothing but my VQ n cap. So this is what we essentially try to do, but we are doing it analytically with vectors written in INJ components. But graphically, this is what we are trying to do. We attach a non-rotating translating axis to P. Once we attach that, the same velocity gets transferred to Q. So we have Vp plus Vp with respect Q with respect to P gives me Vq. And this velocity is invariably perpendicular is what we saw. So that is what it is. Graphically, that is what it is. Now let us see how it comes about when we write it in as unit vectors and solve it using vector algebra. So this is what we are trying to do. So let us do it using vector algebra. So the first question asks, let R Q with respect to P represent the position vector of point Q with respect to point P. What is the X and Y component is what is asked. So we know that this is R Q with respect to P. And this angle I have been given as 40 degrees. I have been given that angle to be 40 degrees. So this is point Q. So R Q. with respect to P is nothing but, what is this distance? 1.2. So it is nothing but 1.2 cos 40 I cap plus 1.2 sin 40 j cap. So we have this. So what will this come out to be? So this is 0.919 I cap plus 0.77 j cap. So I have got this value now. So the 0.919 and 0.77. So let me populate this also. So this is 0.919 meters per second. Sorry, meters. This is a position vector. 0.919 and 0.77. Now what else has been asked? The magnitude of the angular velocity of point Q is asked, and the magnitude of the angular velocity, absolute velocity of point Q is asked. So what have we been asked? The magnitude of absolute velocity of point Q in meters per second and the magnitude of angular velocity of this link, of this rigid link, is asked. Now from relative motion analysis, I can write R, I can write R, Q is nothing but Rp plus Rp with respect to Q. Therefore, Vq is nothing but Vp plus Vp with respect to Q, which is nothing but Vp plus omega cross R. Omega PQ cross R P with respect to Q. This is what we saw earlier. Okay, now that we have this, it is just a matter of substitution now. So I have this VQ is equal to this quantity. I have this. So on substituting, let me erase this. What is it that I know about VQ? VQ is this. Let me copy and paste it here. So this is my VQ is equal to VP. Do we know VP? VP we know here. Plus, let us consider omega. Let the angular velocity vector be represented as omega PQ K cap. Let me take it that it is in this direction, in the positive direction, coming out of the plane of the paper. If it is incorrect, my answer will be negative if the direction needs to be reversed, which we have done umpteen number of times. So this gives me omega PQ K cap. This won't come. Plus omega PQ K cap cross R P with respect to Q. This is the vector. So this is my vector that comes in the cross product. The entire crossed. Now it is just a matter of solving, grouping and solving. So we know if this is I, j, k. If it goes around in this direction, it will be positive. If it is the other direction, it will be negative. So with that in mind, can we just solve this? So this will be VQ. So this will be VQ cos 75I plus this is nothing but this plus, I'll put it somewhere, I'll put it here. Let me keep that here. So what will this mean? K cross I will be J, and then K cross J will be minus I. So let me write the minus I component first. So this will be, it will be minus 0.77 omega PQ I plus 0.919 omega PQ J cap. This let me remove. Now I can group the items. If I group them separately, I get VQ cos 75 is nothing but 0.3 minus 0.77 omega PQ, and then VQ sin 75 is nothing but 0.919 omega PQ. So this equation I got by grouping the I terms. The second equation I got by grouping the J terms. Now there are two unknowns. One is the magnitude of VQ, another is the magnitude of the omega, angular velocity of the link. And we have considered that to be in this direction with positive k cap. If that answer comes out negative, it will imply it was minus k cap. So it is two equations, two unknowns. We know how to solve this. Let us quickly solve this. I can write this as cos 75 plus 0.77 sin 75 minus 0.919 into VQ omega PQ. And what will the right side be? It will be 0.3 and 0. If we multiply this thing out, we'll get the same equation. I've just written it in matrix form. So that with the calculator, I can easily take the inverse. So here, this will be equal to this inverse into this, which is comes out as, what will this be? Cos 75, 0.77 sin 75 minus 0.919. So this comes out to be 0.28 and the other one comes out nearly close to 0.3. So therefore, velocity of Q, the magnitude is nothing but 0.28 meters per second. and omega is nothing but 0.3 k cap in radians per second, because we have got a positive answer. We have got a positive answer. Positive answer does not imply that it is anti-clockwise. It implies that whatever direction we took initially is correct, which we have taken it as anti-clockwise. So this value is okay. So we can populate this in the answers. So the magnitude of absolute velocity is 0.28 meters per second, and the angular velocity comes to 0.3 k cap. But the magnitude is asked. Radians per second. So looking at the next question, a disk of radius r is pivoted about a point here on its periphery. So it is on the diameter of the disk. It is on the circumference of that disk. That it is pivoted here with a frictionless hinge and rotates in order to move the platform H. So as this rotates at some other point, at some other instant of time, it would be like that. It will be like that, and we can see that H, this platform moves. This is the initial position of the platform, and after some time it would have moved like that. The dotted one is after some time, and it is constrained to move vertically with the positive x and y as shown. So this x and y is given. Okay. So now if I were to remove these two, I can just delete it. So what is it that we know here from the analysis of the geometry? We know this is r, and this is given to be theta. So this distance, I know what it is. So from the problem, I can write h is nothing but r plus r cos theta, because this distance is r cos theta. So once we have this relation, we can find out all the unknown velocities and accelerations in the problem. So this is essentially a problem of absolute motion. So what is it that we have been asked? The correct expression for the angular velocity of the disk is asked. So if theta so the correct expression for the angular velocity is asked. So if this is theta, we know how to find the angular velocity of an object. We scribe a line and then we note its change, time rate of change with respect to a fixed reference. So we have this relation here. This is my geometric relation. So I take the time derivative. So h dot will be r dot plus, now I have to apply product rule here because there are two quantities. So it will be r dot cos theta minus r theta dot sin theta. So I have this as, now I know that the disk is a rigid body, so r dot is 0. Both these quantities go to 0. Therefore, h dot is nothing but minus r theta dot sin theta. Why this is negative, we can see from the constraint of the problem. If theta decreases, then h increases. H will go up. So that is why this negative sign has come in. So therefore from here, theta dot I can write it as minus h dot upon r sin theta. So let us see which is the answer. So I have theta dot is equal to r sin theta. Now the next question asks, given that the radius of the disk r is 0.75 meter, what is the magnitude of acceleration of the platform? Basically what we are trying to find out is h double dot, time rate of change of the velocity of the platform at some instant when theta, theta dot, theta double dot are 37, 0.85 and minus 2 respectively. So these values are given. So we have been asked to calculate theta double dot at this point. So from the same relation, if I were to take the time derivative again, now again I fix one and take the derivative of the other two in rotation cyclically. Sin theta minus r theta double dot sin theta minus r theta dot squared cos theta. But again I have this constraint that r dot is 0. So therefore h double dot comes out to be r theta dot squared cos theta. Now the question says, so this is my expression for the acceleration. I can see it is just a degenerate case of circular motion. I have my centripetal acceleration and my tangential acceleration. So if I copy, so I have this as the relation. So h double dot is nothing but r minus r theta double dot is given to be minus 0.2 sine 45 minus into 0.85 squared cos 45. So h double dot comes out to be so h double dot comes out to be minus 0.277 meters per second squared. Now in the question the magnitude is asked, so therefore the magnitude of this h double dot magnitude is 0.28 meters per second squared. So that is my answer. Now the next question asks, if it is known that the platform moves upward with a constant velocity. A set of non-rotating translating axes attached to the disk center can be considered as inertial frame of reference or not. Now let us see this. That is, let us say I have my set of axes like that. I can see that after some time t, it would after some time t, it would have to translate in a circular path. After some other time, it will be like that. So I can see that this is tracing a circular path by virtue of r being fixed. So once something is tracing a circular path, it necessarily has to have centripetal acceleration, in which case it cannot be inertial since it is having a non-zero acceleration. So this is false. Okay, so let us look at this problem. A rigid bar rolls down a circular path so we have a rigid bar like that. It rolls down a circular path onto a horizontal floor. So we have a circular path till this point, and then we have a horizontal floor. The absolute velocity of point C is of a 1.5 meter bar is 6 meters per second to the right. So it is like that and is constant for a time interval, including the instant depicted. So VC is 6 meters per second is what is given. AC, acceleration of this point C is 0 is what is given because it is constant. Neglecting the time of the effect, neglecting the effect of the diameter of the small wheels and friction, answer the following questions. So what are the questions that are asked? What is the magnitude of the absolute velocity of D? Absolute velocity of this point D is asked. The angular velocity of the bar CD is asked. So what is the angular velocity of this rigid bar? The magnitude of acceleration normal to its path, the magnitude of acceleration of point D tangential to its path, and then the angular acceleration of this bar is asked. Okay, so let us see this. What is it that we know about this problem? So if I take this, now let us sketch everything that we know as of now. I know that velocity of this point. I know that Vc is nothing but 6 I cap. Acceleration of c is 0. So this much I know. It is given in the problem. Now we have been told that this point D, it traverses this circular path. So at any instant, I know that this has to be the direction in which my velocity is. It is tangential to the path, tangential to that circular path. And then the normal to this is along that. So let me call this NT, let me call this NN. So NN is normal to path, NT cap is tangential to the path. Now I know that this angle is given to be 40 degrees. So I can clearly see that this angle is also 40 degrees. And then this angle is 50 degrees from the geometry of the problem itself. So this much I know. Another thing I know is that this velocity of point D has to have only components along this direction. It cannot have any other velocity. So I know that velocity of D vector is nothing but nt cap, since it has to travel in that circular direction. Another thing I know is the acceleration of D. Now the acceleration of D, essentially the acceleration of some point which is traversing a circular path. So it will have one tangential acceleration along nt and a centripetal acceleration along nn. So my acceleration of point D is nothing but AD tangential, which will be nt cap, plus AD centripetal, which will be along nc cap. So this much I know. So I know all the directions, the magnitudes. So I know all the directions, but the magnitudes I need to evaluate. Okay. So let us first populate what these vectors are. So from the figure, I can write that nt cap. In x and y system, I can write nt cap as this plus this. So y component will definitely be negative. X component will be positive. So this is nothing but cos 40i minus sine 40j cap. Similarly, nc cap can I write? Now I have this as the vector, the unit vector, which is making an angle 50 degrees with the positive x. So this I can write as cos 50 I cap plus sine 50 j cap. So let us also evaluate this. This will be cos 40. So 0.766 I minus sine 40 is minus 0.643 j cap, and nc cap is cos 50 0.643 I sine 50 is 0.766 j. So I know these two now. So let me also substitute this and get the values for these. So this will come out to be nt cap. So this is 0.766. So I have that vector in component form with Vd as the unknown, which I need to evaluate. Similarly, I can write acceleration also. Which I can write as ADT AD tangential, n cap is 0.766. So this will be 0.766 AD tangential plus 0.643 AD centripetal I cap plus 0.766 ADC minus 0.643 AD tangential J cap. So this is my acceleration of D. So I have got these two vectors in component form. Now what remains is to calculate VD, ADT, ADC. That is what is asked, in addition to one more component. So from relative motion analysis again, I know that R, what are these 2 points? C and D. Okay, there is one more thing. We can, if we take like that, and then we draw this perpendicular here. So if this is beta, let me call this angle as beta. In such a case, I can see that this angle is also beta. Now can I write what beta is? So from this figure, if I write sine beta, is nothing but this distance divided by 1.5. So what is this distance? It's nothing but 0.7. This is 0.7. And then this is 0.7 cos 40. So this is 0.7 minus 0.7 cos 40 divided by 1.5 meters. So therefore beta in here is 6.268 degrees. So we know that from the problem that this is 6.268. Okay, so in such a case, if we take this position vector r of c with respect to d, it will have this as the x component, which is positive, which will be 1.5 sine beta. This is the x component, and then this is the y component, which is negative, which is 1.5 cos minus 1.5 sine beta. So from relative motion analysis, we can write this as AC RC RT plus RC with respect to D, and then differentiate it. Similarly, we can get velocity of C is nothing but velocity of D plus omega CD cross R C with respect to D. And for acceleration, we can write AC is nothing but AD plus omega CD cross omega CD cross R C with respect to D plus alpha CD cross R. c with respect to d. I've just done the time derivative. So I know this. So let us use this first. If you use this equation first, and let us substitute. So we know Vc. Do we know Vc from the problem? We know Vc to be 6 I cap. So Vc is 6 I cap. Velocity of d, we have found it out as this quantity with the unknown Vd still over there. So this is velocity of Vd plus, let us take, let omega Cd vector be and alpha Cd vector be alpha Cd k cap. Let us take both to be positive for now. So this will be omega Cd k cap cross Rc with respect to d. Now from the figure, I can write Rc with respect to d is 1.5 cos beta in the x direction minus 1.5 sin beta in the y direction. So this is 1.5 cos 6.268 I minus 1.5 sin 6.268 J. So let us open this product out. So this is 0.7. I can just write it just like that. Duplicate. And this will be k cross j is minus I and k cross I is plus j. So I have this as plus 1.5 omega Cd sine 6.268 degrees I, because this minus and that minus got cancelled, and then this will be plus 1.5 omega Cd cos 6.268 J. So I can group the I and J terms now. This gives me 0.766 Vd plus 1.5 omega Cd sine 6.268 I cap plus 1.5 omega Cd cos 6.268 minus 0.643 Vd J cap. So I can group the I and J terms now. So this will give me two equations and two unknowns. So I can write this as a matrix form. Again, it will be 0.766 into Vd, and this is omega Cd. This will give me what is on the right side, it is 6, and the other one is 0. And this is 1.5 sine 6.268. And then for Vd, it is minus 0.643. This is 1.5 cos 6.268. So this will give me this vector is equal to this inverse into that. So this will come out to be 7.17 and 3.09. So therefore we have solved for the velocity of point D. The magnitude is nothing but 7.17 meters per second, and this is along NT cap from the diagram. And omega CD, it has come out to be positive, which implies that the direction we took is correct. And since we took the anti-clockwise direction, we have got this as 3.09 radians per second. 3.09 radians per second along positive k. So these two we have solved. So he had asked the angular velocity of the bar. So this is 3.09. Here we have been asked the absolute velocity. So this is 7.17 meters per second. And this is 3.09 radians per second. Now the acceleration is asked. So same drill we have to do, but with acceleration vector now. So this we can clearly see that it will be a little more involved because there are more number of terms. Now in the question we have been given that AC is 0. So 0 is AD. AD we found out to be this quantity, where ADT and ADC, where these two are still unknowns. That is what we want to find out. Plus omega CD, we know it is 3.09. So it is 3.09. K cap cross this is the vector. So this is omega cross R, and then we have alpha. We have considered alpha to be alpha CD K cap plus K cap. So it will be plus alpha CD K cross the same vector. Now there is something interesting here to see, that in this equation we have ADT, ADC and alpha CD. So there are three unknowns, whereas grouping I and J terms will only give us two unknowns. So it appears that it cannot be solved just like that. So there is something more in the physics that we have not looked at. So let us try to look at that. Now for this point D, we know that it is tracing a circular path. So this is having a centripetal acceleration along n cap, nc cap. So in the solution, I have taken this to be nc. So let me mark them as nc so as to avoid confusion. Here also I have taken it as nc. Now this centripetal acceleration, if I know the velocity of point D, I can calculate the centripetal acceleration with the center here. So that is the additional equation that I have. So from here, since D traces a circular path, I have acceleration centripetal, or let me write it as AD. ADC is nothing but VD squared by R. Now this R is the radius of that path. It is not the actual length of the bar, that we must understand clearly. Since this is the circular arc it is passing, so this has to be R. This distance is R. R is 0.7. VD we know what it is. VD we just found out that it is 7.17. So in such a case, I'm in a position to calculate this. This is 7.17 squared by 0.7. So this comes out to be by 0.7. So this comes out as 73.44 meters per second squared along ANC. So this is coming from the physics of the problem. This is an additional equation that we have got. Now we have already got one value. The value for this we have got. So this is solved for. The only unknowns remain ADT, tangential, and alpha CD. So that is what we need to solve for. So let us go ahead and do that. So let me take this equation, put it here. And in this, let me substitute into 73. And then I have this as 73. Now it is just a matter of solving this and finding out what ADT and alpha C are. So there are two equations, there are two unknowns. So this I leave it as an exercise. And when I upload this sheet, I'll solve this completely and I'll upload so that you have something to refer back to. So I know normal to this path is 73.44. So these two I will populate. You can give it a try and then look at the sheet when I upload this to see if you have got the correct answer. So this I'll leave it as an exercise as of now. Otherwise, the entire time will get spent on solving this. So let us look at some more additional examples in that time. Okay, so this question says a right-angled slotted arm is pivoted and pins A and B are considered to move in the slots. So we have a slotted arm which has 90 degrees here. So this has two slots where these pins are actually moving and they are making this slotted arm rotate. For the velocity of pin A as marked, if pin A is going up like that, which of the following is the correct expression for the magnitude of velocity of pin B? Now we can clearly see that if this goes up like that, the bar would rotate like that. So the pin has to go towards this. So we have been asked what is the magnitude of that VB. This is VB. We have been asked what is the magnitude in terms of VA and what we know from the geometry of the system. So let us look at that. Now from here, From here we can see that this distance is XA, this is HA, and in this configuration XA remains fixed. We have a pin and then we have the path where the pin moves. So that distance is fixed, whereas HA is variable because the pin is actually moving along this slot. In the other case, we have XB, which is varying, which is the distance of the pin from this reference. Whereas this slot which is there from that pin, that distance is fixed. So we know that HB and XA are fixed quantities. Okay. So from the figure, can I write tan theta? Tan theta is nothing but HA by XA. Now, another way to look at this is that it has been given that it is right angled. It is given that this is a right angled arm. So if this is 90° and if this is theta, then I can clearly see that this is also theta. So from there, I can see that this is also equal to XB by HB. When I take tan of this theta, it gives me XB by this distance, which is HB. So I've got this relation as HA. So I've got a relation that HA by XA is nothing but XB by HB. So let me cross multiply this. HA HB is XA XB for this problem. So this is the equation that it must respect in order to hold on to the geometry of the problem. So if I take the time derivative, I know by product rule that HA dot HB plus HB dot HA is XA dot XB plus XB dot XA. I've just applied the product rule. But from the figure, I know that XA and HB are fixed quantities. Equals 0. And I know that HA dot is nothing but VA. And XB dot is VB. So therefore, HB dot, this term goes to 0 and this term goes to 0. So I have only this equal to this. Now my idea is to find out VB, which means I need to find out XB dot. So from here, I can clearly see that XB dot is nothing but this quantity divided by XA. And HB I can replace by, sorry, HA dot I can replace by VA. Using this. So therefore, XB dot, which is nothing but VB, is given as HB by XA into VA. So this is just a constraint motion absolute analysis problem. So as to get some practice on how to write the geometrical equations and then subsequently differentiate them in order for us to get the exact quantity. So HB by XA, HB by XA into VA is VB. So we have our correct answer here. Okay. So let us look at this question. the side view of a large window. So we have a window here which is having a pivot there. So that window is opened by using this hydraulic cylinder from where a piston comes out, and this is the cylinder. So this is a variable quantity. So as this increases, the window will rotate like that. That is the idea. So as this reduces, the hydraulic cylinder will go straight and the window will possibly close. So the side view of a large window OP, this window can be opened using is being opened using a hydraulic cylinder CD as shown. The hydraulic cylinder extends at a constant rate of 0.7. So what does this mean? If this distance is S, so S dot is constant at 0.7 meters per second. It is increasing. And it is constant, which implies that S double dot is 0. So at theta equal to 45 degrees, we have to determine some of the quantities. So we know this distance is 2.5 meters. So we have one triangle formed like that, where one side is 0.75, one side is 2.5, and the other side is S. And the angle inside that triangle, one of the vertices, the angle at one of the vertices is theta. So this is again an absolute motion analysis. So once we write one equation from the geometry, we need to subsequently differentiate it in order to get the other quantities. So let us look at this. Now from this circle, let me draw this circle. From this triangle, let me draw this triangle. Let me take it out here. I know that this is S. This is theta. This is 0.75 meters. And this is 2.5 meters. This is point O, this is point C, this is point D. Now I have this triangle with me. So can I apply the cosine rule? So what does the cosine rule say? If I have a triangle like that, let us say this is A, B, C, and this is some beta. So what does cosine rule tell me? So the cosine rule says that C squared is nothing but A squared plus B squared minus 2AB cos theta. So this is what the cosine rule tells me. Okay, so using that, can I write the cosine rule for this triangle? So for this, it will be S squared is equal to 2.5 squared plus 0.75 squared minus 2 into 2.5. This is 2.5, right? Yeah. 2 into 2.5 into 0.75 cos theta. Actually, here I should have written beta since I have labeled this as beta. So I hope that that is clear. There is no confusion there. So let me simplify this. So I have written the cosine rule for this triangle now. This is my cosine rule. Okay, so this gives me S square is nothing but 2.5 squared plus 0.75 squared minus, what is this quantity? 5, 15 fourths, which is 3.75 cos theta. Okay, now at what has been asked, let us look at what has been asked. the length of the hydraulic arm S in meters at the given instant. When is the given instant? When theta is equal to 45 degrees, we have been asked. When this angle is 45, we have been asked what is the measure of S in meters. So we can clearly see from here that S squared will come out to be, at theta equal to 45, will be 2.5 squared plus 0.75 squared minus 3.75 into cos 45. So this comes out to be 4.1608, or S comes out to be root of this, which is 2.039. So this is nearly 2.04 meters. So this is my S at theta equal to 45 degrees. So I have got this very well. So once I have this, what else is asked in the question? It is asked the angular velocity of the window. So what is the angular velocity of the window? We can see that about this pivot, it is rotating with this angle theta. So theta dot is my angular velocity of the window. Similarly, theta double dot is angular acceleration. So we have to differentiate it twice. So let us go ahead and do that. So I have this as my cosine rule. So when I differentiate this, this will give me 2s into s dot. So I hope that that is clear. 2s into s dot is equal to, these are constant values. They have no derivatives. Their derivatives are 0. So minus 3.75 into cos theta dot. I'm yet to take the derivative of that. So this will give me 2s s dot is equal to 3.75 theta dot sine theta. So from here, if I solve for theta dot, I get this as 2s into s dot by 3.75 sine theta. So this is the relation which gives me the angular velocity of the window as a function of s and s dot. So I can see that it is dependent not only on s dot but also on s at some given instant, because it is having a varying relation. Okay, so in that case, if can I substitute this? So theta dot will be 2 into s, we have just found out here to be 2.04 meters. So I can substitute that. So it will be 2.04 into s dot. In the question, s dot is given as 0.7. So this is constantly extending at a constant rate of 0.7 meters per second. So this is 0.7 divided by 3.75 into sine 45. So this gives me theta dot as divided by 3.75 into, so this is 1 point. So this comes out as 1.08 radians per second. And this is coming out to be positive. So what does that mean? Since this is the measure of s, since this is the measure of theta, as n increases, theta also increases. So with s dot increasing, with s increasing with a velocity of s dot, theta also increases. But can we say the same thing about acceleration is a question to be answered. We should never gauge acceleration from the figure, because we can't. It always has to come from mathematics, unless there is some circular motion involved, in which case we can easily gauge the centripetal acceleration direction as we did in the previous question. But otherwise speaking, magnitude, whether acceleration is positive or negative, cannot be gauged as such unless we do work out the mathematics. So if I take this equation, so I have this as one of the answers. So this came out as 2.04 meters, and this has come out as 1.08 radians per second. Now let us see what theta double dot is. So if I take this here and I differentiate this again, so it will be 2s dot into s dot plus 2s s double dot is nothing but 3.75 into theta double dot sine theta plus 3.75 theta dot squared cos theta. So I have just used the product rule. Now the question gives me that s double dot is 0. Okay, actually this, now the question gives me that s dot is 0. So I can further simplify this. So what does this give me? 2s dot squared is nothing but 3.75 theta double dot sine theta plus 3.75 theta dot the whole squared cos theta. Now can I solve for theta double dot here? So theta double dot is nothing but 2s dot squared minus 3.75 theta dot squared cos theta divided by 3.75 sine theta. So this iteration I have got. So let us just substitute what the values are. So this I have it as 0.7, which is constant as given in the question, minus 3.75 into theta dot. Theta dot I got it as 1.08 squared into cos 45 divided by 3.75 into sine 45. So this is my angular acceleration of the window. So let us calculate that. So this comes out as minus 0.796, which is close to theta double, which is close to saying that theta double dot is minus 0.8 radians per second squared. Now we can see that we could not have gauged that actually it is slowing down. This intuition we wouldn't have got, that it is slowing down. So it is very essential that we should not automatically associate acceleration directions on our own. It should come from the mathematics of the problem. Velocity can be done, but accelerations is not an intuitive thing to write. So if velocity is positive, it need not be that acceleration also is positive. Naturally, this tells us that as this s is increasing, the window, although it's angular, it is having angular velocity, but this angular velocity is slowing down with time. And this comes out as minus 0.8 radians per second squared. So this is theta double dot. This is theta dot, and this is s. Okay. So let us look at the last problem. I won't solve it fully, but I'll just give a brief idea about. I won't solve it fully, but let me just give a brief idea about how it is to be solved. Okay, so a weight is suspended on a pivoted disc. So we have a disc which is pivoted here. I can see that there is a pin, a hinge, and then I have this disc like that. Okay, so a weight is suspended on the pivoted disc and it is moving in the direction shown with a constant velocity v is equal to 0.4 meters per second. So I've been given that this weight is moving down with a constant velocity v, and this is connected, tied to this pivoted disc. A, a point on the periphery of the disc, this point A on the periphery of the disc connects to a rigid link whose other end is connected to a slider block. So we have initially a disc which has another disc infused onto it. To that, there is a weight suspended which is moving down. And a point on this periphery is connected to this rigid link. So there is a rigid link which is whose one end is connected at A and the other end is connected to a slider block which is constrained to move in this direction. So with the positive coordinate axis shown, calculate the following when this actual rigid link is horizontal. So some moments before this point would have been here. So it would have been like that. At a moment just before this, so at a moment just before this point would have been here. Point A would have been here. And then if I take this length as the length of AB, now this length is constant because this is a rigid link, right? So now if I were to move this here and then draw a circular arc, since I have this as the path, this is my path, so this necessarily has to be along that direction only. So if I were to draw a circular path, so this would have been my point B at some instant just before this, just before it became horizontal. So that is how it is. All right. So let us see what the magnitude of the velocity of pin A is. And then we have been asked total acceleration of pin A, magnitude and velocity of the slider, magnitude, angular velocity of the rigid link, angular linear acceleration of the slider block is what is asked. Okay, so let me remove this. Now let us see what do we know from here. If I label this point to be some point P, we know the velocity of point P. Velocity of point P is nothing but V, which is nothing but 0.4 meters per second, pointing that way. Now, since this is a rigid disk, if I know the velocity at one point, I know its angular velocity. I can extrapolate the velocity at any point. So this P divided by this distance gives me omega for the disk. Once I have omega for the disk, it is easy for me to calculate velocity at point A. So velocity at point A. So therefore, omega of the disk is nothing but 0.4 by what is this distance? This distance is nothing but 0.7 by 2, which is 0.35 radians per second in minus k cap direction. Since we have been given x and y, it is rotating in the clockwise direction, so it is minus k cap. So therefore, for this question, I have omega of the disk is nothing but minus 0.4 by 0.35 k cap in radians per second. So this I have. So therefore, velocity of point A is nothing but omega of this disk. This is a vector crossed with r a with respect to center O. Center is O. So essentially this vector, which is nothing but 0.6 j cap, which is nothing but minus 0.4 upon 0.35 k crossed with 0.6 j. So I have this also. This quantity also I have. So once I have velocity of point A, then we again go back to our relative motion analysis and find out velocity of point B. Only thing is velocity of point B is constrained to move along that direction now. So what do we know? That velocity n cap is nothing but cos 60 I cap plus sin 60 j cap. This is 60 degrees. This is 60 degrees. So what do we know about velocity of B? Is nothing but the magnitude n cap. And we know acceleration of B. It is not moving in a circular path, it is moving in a straight path. So it can have only one component, which is normal. So this also has to be along n cap. And then from relative motion, now that we know this, we don't know these quantities that we have to find out. So we will use our relative motion analysis. So using relative motion, I can write velocity of B is velocity of A plus omega link cross R B with respect to A. Similarly, acceleration of B, I can write it as acceleration of A plus omega link crossed with this quantity plus alpha of the link cross this. So it is just a matter of substitution with the understanding that AB and VB we know. We know these two, we know the direction, we don't know the magnitudes. VA we know, we just found out. Acceleration of A we can find out because it will be having only centripetal acceleration. It is not having any. The disk is having only a constant angular velocity. So this will have only centripetal acceleration like that, only along j cap. Omega alpha we need to find out. Rest of the quantities we know. So that is how this is to be solved. So I'll write down the final answers in this sheet when I upload it so that people who have taken an attempt can refer back to the sheet and find out if they have solved it correctly. So with that, I have closed. With that, I have run out of questions and also we have run out of time. So I will stop here. So we've discussed quite a lot of examples on relative and absolute motion analysis today. So next week, whatever the axes that we fixed, which was only translating, we will relax that constraint in the next week and let it rotate also. And we will see how to do relative motion analysis with rotating frames of reference, which will come in handy in some problems. So till next week, thank you.